Greek astronomy was still based on the geocentric model. The Earth was still in the center of the universe. And as you'll see more details in the lecture notes and any textbooks, one of the big problems about the geocentric universe was that it couldn't really explain very naturally the movements of planets. It's actually even in the name. The reason why planets have their name is because they didn't just go around the Earth in a nice way, but sometimes they would show what is called a retrograde movement, as you can see here. Sometimes Mars would actually go back a little bit and then back to the normal movement. And we know now, obviously, that this is because the Earth is also going around the sun, and sometimes the Earth overtakes some of the planets, and some of the inner planets overtake the Earth. So there's complications. But back then, the geocentric model was so strong that people went into what you'd call data science to try to solve it. And one of the simplest ways, even though it could be quite complicated, was to actually invoke that planets weren't just going around the Earth, but apart from going around the Earth, they could be orbiting some other circles. And you could create these, as many as you want. This is really not very important for you to know, apart from getting some context, that it is possible to come up with a model where the Earth is in the center of the universe. And if you had some of these epicycles, as many as you want, from the different planets, you can actually make incredibly accurate predictions of where the planets are going to be in thousands of years from now. One thing you cannot actually do is explain essentially the phases of Venus, because in a geocentric model, you wouldn't expect to see phases, right? So the sun would always be further away from Venus, and therefore there is no way that you could see a full Venus or essentially a dark Venus, as we can see in reality. So when telescopes came around, they really challenged the geocentric view, but from a kind of a data science perspective, this complicated model would actually still work. It is wrong, but it can still work. So in fact, what happened during the 15th century and after that was sort of the heliocentric revolution. We realized that actually at the center, we had the sun, and that very simply, this model would predict or would explain why Mars actually seems to go backwards. That happens when essentially the Earth overtakes Mars, because Earth is an inner planet when compared to Mars, which is outside. So nowadays, and even though we've covered in detail, and again, you should go through the steps in the lecture notes and get in touch if anything is not clear, you can actually define 1AU by looking at some things you can measure from the ground using the moon and the position of the sun, the moon, and the Earth system. The modern way to define 1AU does not use those measurements. Instead, it is based on first measuring the speed of light, then using a radar to get the distance to Venus, and finally using Kepler's laws to actually figure out what 1AU is. And I think it is worth just guiding you through the steps of how you do that. Again, you have it in your lecture notes, and it's also here, but I'll try to explain the basics so you can actually reproduce it and do it yourself. So the most important thing is to understand that the best way to do this is when we can see a transit of Venus, when Venus is passing directly in front of the sun. At that point, we could use a radar, shooting it in the direction of Venus. It should hit its surface and then come back. By measuring the time it took for the radar to go back and forth, because we know the speed of light very well, we know the distance from the Earth to Venus. And if you use Kepler's third law, and we're actually going to recap and use it more in section 3, so that's the following section, what you can do is, if you divide it for the Earth and for Venus, you can get rid of the constants because they will be the same. It's still the solar system. And ultimately, what you can do is to write, just like you can see here, to write the distance of the Earth to the Sun, that's AE, as the distance from the Earth to Venus, that's EV, plus the distance from Venus to the Sun. If you do this, this is why we can write it this way. We can write that the ratio of the periods squared is equal to AE to the power of 3, as it was before, and also in terms of AE minus EV. And EV is something that we can determine with the radar. The other ingredient you're going to need, obviously, is to determine what is a year on Venus. That's the period of Venus. We know that the period of the Earth is 1 year. That's relatively easy. So we can measure the period of Venus in years. So we can use it. There's no problems with units. And we can even define, so this is what I did here. I called Y the ratio between 1 year on the Earth and 1 year on Venus. If you do this, you can rearrange the equation such that you can write it like you can see below. And this essentially defines what 1 AU is, the distance from the Earth to the Sun. So it's given in terms of something that we can measure with the radar during a transit of Venus, that's EV. And in practice, what you measure is the time that the signal takes to come back to us once you shoot it. And also the other thing you need to measure is a ratio between 1 year on the Earth and 1 year in Venus. And if you have questions about any of these steps, just please let me know.